In this lesson, we will delve into the details concerning gear hobbing tools related to task 1.2 inches, project 1. We will explore the basic concepts, working principles, and structural characteristics of gear hobbing tools. Additionally, we will learn about the key points in their design and manufacturing, as well as their application in actual production. By studying these topics, you will gain a solid understanding of the core knowledge of gear hobbing tools, laying a strong foundation for further professional learning and practice. In the field of gear machining, gear hobbing is a highly important processing method, and the gear hobbing tools are the key instruments for executing this process. Gear hobbing tools are primarily used for machining various cylindrical gears and worm wheels, characterized by their high machining precision and production efficiency. From a historical perspective, the emergence of gear hobbing technology marked a significant breakthrough in the field of mechanical manufacturing. It originated from the continuous quest for efficient and precise gear machining methods. Early gear hobbing tools had simple structures, but with the continuous advancement of industrial technology, their design and manufacturing processes have become increasingly sophisticated. The working principle of gear hobbing tools is based on the generating method. The generating method is a technique that uses the principle of gear meshing to machine gears. In gear hobbing, the hob functions like a helical gear with a large helix angle, engaging with the gear being machined according to a specific transmission ratio. Specifically, the rotational motion of the hob is equivalent to an infinitely long rack in motion, while the gear being machined gradually forms its tooth profile during the meshing process with this rack. This motion relationship can be described by the following formula. Let the rotational speed of the hob be n1, the rotational speed of the workpiece be n2, and the number of threads on the hob be k. The generating motion must satisfy the condition n2 divided by n1 equals k divided by z2. The derivation of this formula is based on the fundamental principles of gear meshing. In gear transmission, the rotational speeds of two meshing gears are inversely proportional to their number of teeth. In gear hobbing, the meshing between the hob and the gear being machined also follows this rule. By adjusting the speed ratio between the hob and the gear being machined, gears with different numbers of teeth can be produced. Gear hobbing tools typically consist of the tool body, cutting teeth, and chip pockets. The tool body is the main part of the tool, providing support and positioning for the cutting teeth. The cutting teeth are the cutting components of the tool, and their shape and geometric parameters directly affect the machining quality and efficiency. The chip pockets are used to accommodate the chips produced during the cutting process, ensuring the smooth progress of the cutting operation. The main geometric parameters of the cutting teeth include the rake angle, relief angle, and helix angle, the angle between the rake face and the end face of the hob. The size of the rake angle affects the cutting force and the cutting temperature, and it is generally selected based on the properties of the material being machined. The relief angle is primarily used to reduce friction between the tool and the workpiece. Thereby, extending the tool's lifespan. The size of the helix angle, together with the helix angle of the chip pocket, determines the direction of chip flow and the direction of the cutting force. For example, for materials with higher hardness, a smaller rake angle is usually chosen to enhance the strength of the cutting teeth. In contrast, for materials with better plasticity, the rake angle can be increased appropriately to reduce the cutting force. The design of gear hobbing tools needs to consider multiple factors, such as the parameters of the gear being machined, the required machining precision, and the cutting conditions. In the design process, the basic dimensions and the geometric shape of the hob must first be determined based on parameters such as the module, number of teeth, and the pressure angle of the gear being machined. Manufacturing gear hobbing tools requires high-precision machining equipment and processes. Generally, the manufacturing process of a hob includes the following steps: blanking, forging, rough, turning, gashing to form the relief angle, heat, treatment, grinding the bore-orient face, grinding the tooth top fine, grinding of the cutting edge coating. The heat treatment process significantly impacts the performance of the tool, as it can enhance the hardness, strength, and wear resistance of the tool. In actual production, different manufacturers may adopt different manufacturing processes and techniques, but all aim to improve the performance and the quality of the tools. For example, some advanced manufacturing processes can achieve a lower surface roughness of the cutting teeth, thereby improving machining precision. In the automotive manufacturing industry, gear hobbing tools are widely used for machining engine gears, transmission gears, and more. For example, in the gear machining of a certain automobile engine, using gear hobbing tools can efficiently produce high-precision gears, meeting the engine's requirements for gear transmission precision and reliability. In the field of machine tool manufacturing, gear hobbing tools also play a crucial role. The spindle gears and the feed gears of machine tools need to be manufactured through gear hobbing. By reasonably selecting gear hobbing tools and the machining parameters, the machining precision and the performance of machine tools can be improved. From the development history and the working principles of gear hobbing tools, we can deeply appreciate the wisdom and value of traditional craftsmanship. The generating process principle as a classic mechanical design concept continues to play an important role in modern manufacturing even after a century. This tells us that traditional craftsmanship is the cornerstone of modern manufacturing, and we should inherit and promote this valuable wisdom. At the same time, with continuous technological advancements, we must also keep innovating. In the design and manufacturing of gear hobbing tools, it is essential to continually introduce new materials, processes, and technologies to enhance the performance and the quality of the tools, thereby meeting the demands of modern manufacturing for high precision and high efficiency machining. In this lesson, we primarily studied topics related to gear hobbing tools. We began by understanding an overview of gear hobbing tools, including their significant role in gear machining and their historical development. We then focused on the working principles of gear hobbing tools, which are based on the generating process, achieving gear machining through specific transmission ratio relationships. We also learned about the structural features of gear hobbing tools, including components such as the tool body, cutting teeth, and chip pockets, as well as the geometric parameters of the cutting teeth. Following this, we explored the design and the manufacturing of gear hobbing tools, which involve multiple stages and factors. Finally, through practical application cases in automotive and machine tool manufacturing, we deepened our understanding of gear hobbing tools. At the same time, we have also gained an appreciation for the wisdom of traditional craftsmanship and the importance of innovation from gear hobbing. I hope that in your future studies and work, you will be able to inherit and promote these values.